Hi, my name is Leo, and today we'll be looking at genetic mapping. Here we have a potential genetic map for the phenotypes of tail rings, ear shape, and face color in the red panda. Our alleles show us that a ringed tail is dominant to solid tail, pointed ears are dominant to round ears, and a red face is dominant to white face. Our parent generation will be crossing a homozygous dominant with a homozygous recessive panda. This is what their potential chromosomes would appear like. The generation that we obtain from this is the F1 generation, and this panda would be heterozygous, but would have the phenotypes of the dominant parent. Next, we will perform a test cross by crossing our heterozygous offspring with a homozygous recessive offspring. The reason why we do this is to find the potential probability values for the different phenotypes and genotypes of our offspring, taking into account crossovers. First potential crossover is a single crossover, which will happen in either the R1 or R2 sector. The genotypes obtained from a single crossover 1 are little t, big E, big F, and big T, little e, little f. Our single crossover 2 genotypes are big T, big E, little f, and little t, little e, big F. The next type of crossover is a double crossover, in which a cross happens in both the R1 and R2 sector. Our genotypes for this are little t, big E, little f, and big T, little e, big F. Here we have our genetic map, and as you can see, the R1 distance is 4 centimorgans, while the R2 distance is 8 centimorgans. The distance shows us the potential probability for a crossover to happen, where the greater distance is a higher probability for a crossover. Our coefficient of coincidence is 0.71. To find the probability of a double crossover, we will take the R1 and R2 distance and multiply both of those by the coefficient of coincidence value. We will then multiply by 0.5 and finally by 100 to obtain a percentage. To obtain the probability of a single crossover 1, we will take our R1 distance and subtract our value from our double crossover probability. We will then multiply by 0.5 and then finally 100 to obtain the percentage. Here we have a chart showing the phenotypes, genotypes, probabilities, and event types for each type of crossover. As you can see, a no crossover event has the highest probability at 44, while a double crossover event has a very low probability at 0.11%. It is worth noting that a single crossover 2 event has a higher probability because the distance of the R2 sector is greater than that of the R1.